The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Hi. Today we're going to learn a rather powerful technique called the technique of partial fractions that's particularly applicable for one special type of integrand. In particular, it's going to be applicable to the situation where the integral has the form, the quotient of two polynomials. In other words, suppose we have integral p of x dx over q of x, where p and q are both polynomials in x. And by the way, for reasons that will become apparent later, we'll assume that the degree of p is less than the degree of q. In other words, that the highest exponent in the numerator is less than the highest exponent in the denominator. By the way, if that's not the case, we can always carry out long division first and carry out enough terms until we get a term in which this is the particular case. You see, I'll make that clearer as we go along, but for the time being, all we really care about in terms of outlining this form, and again, as we will often do in these types of techniques, the place that we'll pick up the real fine computational points are in the exercises. We'll use the lectures to just sort of outline what the technique is and how it's used. But suppose now that we have the quotient of two polynomials, and we want to integrate it. Now the idea is this. There are two key steps that dictate this particular method. The first thing is that we saw in the last lecture that we can handle denominators if they involve nothing worse than linear and quadratic polynomials. In other words, we know how to integrate something like dx over x plus a constant. We know now how to integrate dx over ax squared plus bx plus c. So we know how to handle that type, okay? And the second important thing, and I'll amplify this too as we go along, the second important thing is that theoretically, every real polynomial can be factored into linear and quadratic terms. Now this is a little bit misleading if you try to read more into this than what it really says. It doesn't mean that we can always find a factorization quite simply. In other words, we may at best be able to approximate a root. We don't have to use things like we've talked about in the notes so far, Newton's method and things like this, linear approximations, tangential approximations. We may have to approximate the roots. But that theoretically, if a polynomial with real coefficients has degree greater than 2, it has at least one real root. In other words, we can keep factoring things out this way. The only thing we can't do is to guarantee that once we get down to a quadratic, that we can get real roots out of this particular thing. In fact, the classic example is to visualize x squared plus 1. In other words, we can't factor x squared plus 1 unless we introduce non-real numbers. Remember the technique, you can write that x squared plus 1 is x squared minus I squared, where I is the square root of minus 1, and this factors into x plus I times x minus I, etc., but these are non-real numbers. In other words, you can't always factor a quadratic to get real numbers. In fact, if you recall the quadratic formula, you have this square root of b squared minus 4ac. If b squared is less than 4ac, what's inside the square root sign is negative, and that leads to non-real roots. So you see, we can't always factor quadratics into real factors. By the way, don't identify things that were difficult to factor with things that can't be factored. You know, a lot of times we think of, say, here's an example I thought you might enjoy seeing here. Take, for example, x to the 4th plus 1. That looks something like it belongs to the family x squared plus 1, and x squared plus 1 can't be factored. You might think that x to the 4th plus 1 can't be factored. Now again, it's not important that you understand what made me think of these tricks or what have you. What I do want to show is that even situations where the polynomials might look like they don't factor, they really do. For example, with x to the 4th plus 1, we can write this in the disguised form x squared plus 1 squared. So that's what? X to the 4th plus 1. But there's a middle term here of 2x squared. so I subtract off the 2x squared. Now this has the form, the sum and difference of two squares, namely x squared plus 1 squared, and also the square root of 2 times x squared. In other words, I can write this as this plus the square root of 2 times x times this minus the square root of 2 times x. Observing that even though the square root of 2 is an irrational number, it is nonetheless a real number. The important point that I want to point out, though, as far as setting up this technique called partial fractions, is that whether it's easy or not easy, the fact remains that when we have a polynomial in our denominator, it can always be factored into a combination of linear and quadratic factors, okay, using real numbers. Well, it's difficult to factor some of these things, so by way of illustration, let me pick out one that comes factored. Let me start with a particular problem here. Let's take the integral dx over x minus 1 times x squared plus 1. See, what is the integrand in this case? It's 1 over x minus 1 times x squared plus 1. Now, the idea is this. See, here's a quadratic factor. Here's a linear factor. What fractions do I have to add to wind up with something like this? Well, again, and this is going to be another example of our old adage that it's easier to scramble an egg than to unscramble one. You see, given two fractions, it's one thing to find their sum. Given the sum, it's quite another thing computationally to find what fractions you had to add to get that sum. The idea is this. If you wind up with a denominator that has an x minus 1 term and an x squared plus 1 term, it appears that you must have started with terms, say, what? In other words, you must have had one term which had a denominator of x minus 1 and a term which had a denominator of x squared plus 1. Because you see, if I start with these kind of denominators, when I cross multiply and put things over a common denominator, I will wind up with x minus 1 times x squared plus 1. The question that comes up is, what shall our numerators be? And here's the main reason why we pick the degree of the numerator to be less than the degree of the denominator. Notice, for example, in this particular case, the numerator has degree 0. Namely, the highest power of x that appears is the x to the 0 term. On the other hand, the denominator has degree 3. See, there's an x cubed term in the denominator. You see, if there had been an x to the 4th in the numerator, I could have multiplied out the denominator, divided it into the numerator, and just kept carrying out the division long enough until I wound up with a remainder which was less than a degree, less than a cubic. In other words, less than the 3rd degree polynomial remainder. That's not the point. The point is that as long as the degree of the numerator is less than the degree of the denominator, it means that the terms that we're adding must have the degree of the numerator less than the degree of the denominator. See, it's sort of like adding fractions. If you start with one fraction whose numerator is greater than the denominator, then certainly any sum that you get is going to be bigger than 1. In other words, if you want to wind up with dealing with positive numbers, and you want to wind up with a fraction which is less than 1, it stands to reason that all the fractions that you're adding must be less than 1. So if I'm going to wind up adding quotients of polynomials to get a sum in which the degree of the numerator is less than the degree of the denominator, it means that every one of the terms in my sum must have this particular property. In other words, with this as a hint, I say, look at, my denominator here is x minus 1. That's degree 1. That means my numerator can't be greater than degree 0. But degree 0 means a constant. So I say, OK, that means that this has the form some constant over x minus 1. Now I look at this denominator. It's quadratic. And I say to myself, I'm starting out with a quadratic. The degree of the numerator can't be greater than the degree of the denominator. Since the degree of the denominator is 2, that means the degree of the numerator can't be more than 1. And the most general first degree polynomial has the form what? Some constant times x plus a constant. So what I'm saying is, OK, to wind up with something of the form, well, to wind up with 1 over x minus 1 times x squared plus 1, I had better start with something of the form a over x minus 1 plus bx plus c over x squared plus 1, where a, b, and c are constants. The key point is that if we weren't sure that the degree of the numerator were less than the degree of the denominator, we would not know where to stop in our numerator. In other words, by this convention, we're sure that the degree of the numerator in any one of these terms can't be greater than the degree of the corresponding denominator. You see, and by the way, notice, for example, if it turns out that we put too much in. For example, suppose it turns out that this numerator here should only be a constant. There's no law against having b turn out to be 0. By the way, again, what these things are called, just to increase our vocabulary, this is called, what I'm going to do now is called the method of undetermined coefficients. You see, what I know is that I must have the form a over x minus 1 plus bx plus c over x squared plus 1. What I don't know is specifically how to choose the values of a, b, and c. And the technique works something like this. What we do is we put this over a common denominator. What will the common denominator be? It'll be x minus 1 times x squared plus 1. How will I put this over a common denominator? It'll be a times x squared plus 1 plus bx plus c times x minus 1. Now, this is supposed to be an identity. Now, if two fractions are identical and the denominators are the same, which is what they will be after I put this over a common denominator, the only way they can be identical is for the numerators to be identical. So you see, what I'm going to do is to cross multiply here to obtain the numerator of the right-hand side, and then I will equate that to the numerator on the left-hand side, which is 1. All right, now what is the numerator on the right-hand side? It's a times x squared plus 1. That's ax squared plus a. Then it's going to be x minus 1 times bx plus c. That's going to be bx squared minus bx plus c times x minus c. And now the idea is something like this, and I'll come back to this in a few moments to hammer this home from a different point of view. What is the coefficient of x squared on the right-hand side of the equation? The coefficient of x squared on the right-hand side of the equation is a plus b. What is the coefficient of x squared on the left-hand side of the equation? And at first glance you say, there is no x squared on the left-hand side of the equation. What that means, of course, is that the coefficient of x squared on the left-hand side of the equation is 0. So what we say is, okay, the coefficients of x squared must match up. Therefore, a plus b, which is the coefficient of x squared on the right-hand side, must equal 0, which is the coefficient of x squared on the left-hand side. In a similar way, the coefficient of x is c minus b on the right-hand side. The coefficient of x on the left-hand side is 0. Consequently, c minus b must be 0. And finally, the constant term on the right-hand side is given by a minus c. On the left-hand side, the right-hand term is 1. Consequently, a minus c must equal 1. What do I wind up with? Three equations with 3 unknowns. Well, there are a number of ways of handling these things. The easiest one I see offhand is I notice if I add the first 2 equations, I wind up with a plus c is 0. Knowing that a plus c is 0, and also that a minus c is 1, it's easy for me to conclude that a must be a half and c must be minus a half. And by the way, now knowing what a and c are, I can use either of these 2 equations to determine b, and b turns out to be minus 1/2. In other words, what does this tell me? It tells me that if I replace a here by a half, and b and c each by minus a half, the right-hand side here will be an identity for the left-hand side. That there will be 2 different ways of naming the same number for each value of x. In fact, doing this now out in more detail, what we've really shown here, in other words, if I replace a by a half and b and c each by minus a half, then I factor the 1/2 out. What I've shown is that 1 over the quantity x minus 1 times x squared plus 1 is equal to 1/2 times the quantity 1 over x minus 1 minus the quantity x plus 1 over x squared plus 1. By the way, I can separate this into 2 terms, each of which has a denominator of x squared plus 1, and I get what? A half times 1 over x minus 1 minus a half times x over x squared plus 1 minus a half times 1 over x squared plus 1. Now, the key is this. I didn't really want this. What I wanted was what? This was to be my integrand. What I wanted was to integrate this with respect to x. Well, if given this identity over here, the integral of dx over x minus 1 times x squared plus 1, recalling that the integral of a sum is a sum of the integrals, etc., can now be written as what? It's 1/2 integral dx over x minus 1 minus 1/2 integral x over x squared plus 1 times dx minus 1/2 integral 1 over x squared plus 1 times dx. Now here's the point. Notice that every one of my denominators now is either linear or quadratic. In fact, without going through the details here again, if I let u equal x minus 1 in this example, this reduces this to the form du over u. In other words, a u to the n du form. If I let u equal x squared plus 1 over here, if u is x squared plus 1, notice that du is 2x dx. So my numerator becomes a constant multiple of du. And again, I have a u to the n du form. And finally, if I look at my last integral here, notice that this is the sum of two squares, which suggests the circular trigonometric functions that we were talking about last time. Or if you wish, you can go to tables and look these things up. They're all in there. But again, without going through the details, because this is the easy part again, it turns out that once you have this relationship here, we can integrate this to obtain log absolute value x minus 1. The integral here is log, natural log, absolute value of x squared plus 1. I can leave the absolute value signs out because x squared plus 1 has to be at least as big as 1. It can't be negative. And finally, either by trigonometric substitution or by memorization or what have you, integral dx over x squared plus 1 is just the inverse tangent of x. In other words, by using partial fractions and reducing a complicated polynomial denominator into a sum of linear and quadratic terms, I was able, by knowing my techniques of last time, to integrate the given expression. And by the way, I would be a little remiss at this stage of the game if I did not take the time to once again reinforce a very important concept. And that is, it may be difficult starting with this to get this. What should not be difficult is starting with this to be able to differentiate it and show that you wind up with 1 over x minus 1 times x squared plus 1. In other words, as usual, with the inverse derivative, once you find an answer and you want to see whether your answer is correct or not, all you have to do is differentiate the answer and see if you get the integrand. But at any rate, this is how the technique called partial fractions works. It works for the quotient of two polynomials, and to make the undetermined coefficients technique work right, you must assume that the degree of the numerator is less than the degree of the denominator. And obviously in the exercises, I'll give you some where the degree of the numerator is greater than the degree of the denominator, and if you don't perform long division first, you're going to get into trouble trying to find the answer to the problem. But all I want to emphasize here is the technique. And by the way, what I want to do before I go any further also is to emphasize a rather special property of polynomial identities. You recall that undetermined coefficients hinged on the following, and I'll pick a quadratic to illustrate it with. Suppose you have two quadratic expressions in x identically equal. In other words, a sub 2x squared plus a sub 1x plus a sub 0 was identically equal to b sub 2x squared plus b sub 1x plus b 0. Notice the technique that we used was, as we said, look, let's compare the coefficients of x squared, let's equate the coefficients of x, and let's equate the constant terms. How do we know that you're allowed to do this? Well, let's see if we can show that this must be the case. For example, let's do this with any calculus at all. Suppose this is an identity. If this is an identity, it must be true for all values of x. In particular, it must be true when x is 0. Notice that when x is 0, the left-hand side is a sub 0, the right-hand side is b sub 0, and we wind up with a sub 0 equals b sub 0. See, the constant terms were equal. Well, if a sub 0 equals b sub 0, we can cancel a sub 0 and b sub 0 from this equation. That leaves us with this equaling this. From this, we can factor out an x and get that x times a sub 2x plus a1 is identical with x times b sub 2x plus b1. If x is not 0, we can cancel x from both sides of the equation, and that shows what? That for any non-zero value of x, a2x plus a1 must be identically equal to b2x plus b1. Once we have this formula established, let's let x equal 0 in here, and we see what? With x equal to 0, that a1 equals b1. In other words, that the coefficient of x on the left-hand side equals the coefficient of x on the right-hand side. You can keep on this way, but a very nice technique to use here is a reinforcement of something that we talked about before. I think it was when we were doing implicit differentiation, and we talked about identities versus equations. You see, if this is an identity, and what do I mean by an identity? That this, we're not saying find what values of x this is true for. By an identity, we're saying, look at, these two expressions are the same for all values of x. They're synonyms. And what we're saying is if these two things are synonyms, their derivatives must be synonyms. And all we're saying is, look at, if you want to use calculus here, differentiate both sides of this expression, and you wind up with 2a sub 2x plus a1 is identically equal to 2b sub 2x plus b1. Since these two things are identical, let's equate their derivatives again. See, the derivative of identities are identical, and we wind up with 2a2 is identically equal to 2b2, and therefore a2 must equal b2. Knowing that a2 equals b2, we can come back to this step and show that a1 equals b1. And now knowing that a2 equals b2 and a1 equals b1, we can come back to the original equation and show that a0 must equal b0. Now you may wonder, why are we making all of this ado over such what appears to be a very obvious thing? And I would like to give you a caution here. I'd like you to beware of something. It's something which works very nicely for polynomials, but doesn't always have to work all the time. In fact, later, when one studies differential equations, this becomes a very important concept, which later gets the name linear dependence and linear independence. We're not going to go into that now, but the key idea is this. In general, knowing that a1u1 plus a2u2 is equal to b1u1 plus b2u2, you cannot say, therefore the coefficients of u1 must be equal and the coefficients of u2 must be equal. Don't get me wrong. If a1 equals b1 and a2 equals b2, then certainly a1u1 plus a2u2 is equal to b1u1 plus b2u2. I'm not saying that. What I'm saying is, conversely, if you start knowing that this is true, it does not follow that they must match up coefficient by coefficient. Okay? And you say, well, why doesn't it have to follow? And I think the best way to do that is by means of an example. For example, in this general expression, let u1 equal x and let u2 be x over 2. Look at the expression 5x plus 6 times x over 2. That's what? It's 5x plus 3x is 8x. Look at 3x plus 10 times x over 2. That's 3x plus 5x, which is also 8x. In other words, 5 times x plus 6 times x over 2 is identically equal to 3 times x plus 10 times x over 2. Yet you can't say, therefore, the coefficients of x must be equal and the coefficients of x over 2 must be equal. In fact, if you said that, you'd be saying that 5 is equal to 3 and 6 is equal to 10, which of course is not true. Okay? So at any rate, I just wanted to show you here the kind of mathematical rigor and cautions that have to be taken if one is going to use the technique called partial fractions, what the key ingredients are. Now, it turns out that not only are partial fractions important in their own right, it also turns out that partial fractions handles a rather difficult type of integral, one that uses polynomials in sine x and cosine x. And the reason I wanted to mention this was not so much because the technique is nice. The technique, by the way, is in the text. But there's something very interesting in the text, the way the author introduces the topic. And I thought that that was worth an aside in its own right. In the section where this thing appears, it says, it has been discovered that. The author makes no attempt to show logically why one would expect that a certain thing is going to work. All the author says is, it has been discovered that. And this tells a long story, that in many cases we wind up with an integrand that we don't know how to handle. We make all sorts of substitutions in the hope that we can reduce the given integrand to a form that we know how to handle. Sometimes we're successful, sometimes we're not. In the cases where we're not successful, somebody, either by clever intuition or what have you, maybe it's just blind luck, stumbles across a technique that happens to work. And I sort of liked this particular example in the text where the author says it has been discovered that. Because to me, it's not at all self-evident, and yet it's a rather pretty result. The result says this. Suppose you make the substitution z equals tangent x over 2. Now, where do you pull this out of the hat from? Z equals tangent x over 2. That's the ingenuity, the experience, the luck. But the idea is, let's suppose that we stumbled across this one way or the other. If we translate this equation into a reference triangle, we have what? That we'll call the angle x over 2, and the tangent is z, so we'll make the side opposite z, the side adjacent 1. That makes the hypotenuse the square root of 1 plus z squared. Now watch what happens when you do this. See, z is equal to tan x over 2. Therefore, dz is the differential of tan x over 2. Remember, the differential of tan x with respect to x is secant squared. But we also, by the chain rule, have to multiply by a derivative of x over 2 with respect to x. In other words, if z is tan x over 2, dz is not secant squared x over 2, it's 1/2 secant squared x over 2 dx. But what's secant squared x over 2? Let's go back and look at our diagram. The secant of x over 2 is the hypotenuse over side adjacent. That's the square root of 1 plus z squared over 1. And therefore, the square of the secant is just 1 plus z squared over 1. See, 1 plus z squared. So with the 1/2 in here, this becomes 1 plus z squared over 2 times dx. And consequently, if I compare these two now, notice that dx is just twice dz over 1 plus z squared. In other words, what's happened to dx? It's been replaced by a differential in z, which involves the quotient of two polynomials. So dx comes out very nicely this way, in terms of what? The quotient of two polynomials. How about sine x and cosine x? And again, notice the dependency on identities. Sine x is twice sine x over 2, cosine x over 2. But from my reference triangle, I can pick off the trigonometric functions of x over 2 very easily. Namely, the sine of x over 2 is just z over the square root of 1 plus z squared. And the cosine of x over 2 is just 1 over the square root of 1 plus z squared. Plugging that in here, I find that sine x is twice z over the square root of 1 plus z squared times 1 over the square root of 1 plus z squared. Multiplying this out, I find what? That sine x is twice z, and the square root of 1 plus z squared times itself is just 1 plus z squared. In other words, sine x is 2z over 1 plus z squared. In other words, with this substitution, what happens to sine x? It becomes 2z over 1 plus z squared, which is also the quotient of two polynomials in z. Okay? Finally, how about cosine x? What identity can we use to reduce cosine x in terms of x over 2? Why do we want the x over 2? Again, notice that even though we may not have invented this substitution by ourselves, once it's invented, the relationship to the angle x over 2 becomes very apparent. At any rate, notice the identity that says that cosine 2x is cosine squared x minus sine squared x, translates into cosine x is cosine squared of half the angle minus sine squared of half the angle. Well, cosine squared x over 2, well, cosine x over 2 is just 1 over the square root of 1 plus z squared, so cosine squared x over 2 is just 1 over 1 plus z squared. Similarly, sine squared x over 2 is just z squared over 1 plus z squared, and what we find is that cosine x is 1 minus z squared over 1 plus z squared. And again, what's happened? Cosine x is now expressible as the quotient of two polynomials in z. In fact, as an application of this, let's come back to an integrand that's been giving us some trouble for quite some time now. let's look at the integral secant x dx and see if we can't use this technique that we've just learned to solve this particular problem. Notice that secant is 1 over cosine. Therefore, integral secant x dx is integral dx over cosine x. Now, let's come back here for a moment just to refresh our memories. We saw that dx was 2 dz over 1 plus z squared. We saw that cosine x was 1 minus z squared over 1 plus z squared. Therefore, 1 over cosine x will just be the reciprocal of this. In other words, coming back here now, we can replace dx by 2 dz over 1 plus z squared, and 1 over cosine x by 1 plus z squared over 1 minus z squared. Okay? Therefore, in terms of this substitution, integral secant x dx is just twice integral dz over 1 minus z squared. But what is this integrand? This integrand is the quotient of 2 polynomials in z. Therefore, I could use partial fractions here, write this as a term, something over 1 plus z plus something over 1 minus z, etc., solve the problem in terms of z, and then remembering that z is tangent x over 2, I can then replace z by what it's equal to in terms of x, and in that way solve the problem. Now you see, what I want you to see again that comes through here all the time is how we are continually looking for ways of reducing integrals to equivalent integrals, but hopefully ones that are more familiar to us, meaning what? Ones that we are able to handle. In the next lesson, we're going to find a very powerful technique which is far more general than partial fractions, a technique which is used over and over again, which is probably the single most important technique. But I won't say any more about that right now. We'll continue with this discussion next time, and until next time, goodbye.
Funding for the publication of this video was provided by the Gabriella and Paul Rosenbaum Foundation. Help OCW continue to provide free and open access to MIT courses by making a donation at ocw.mit.edu/donate.